So what we were talking about last time is what happens to a current loop in a magnetic field. Okay. So this is not just a single segment of current, but I've made a nice rectangular segment. Of course, current usually flows around in a closed loop. So this is something to consider. And we have the external magnetic field as into the page. And what we did at the end of last time was simply just to apply the right-hand rule. We slapped each set current into the magnetic field to get the force direction. And we discovered that the forces in this case seem to pair up so that the force at the top and bottom segment are equal and opposite as long as the field is, of course, the same. The field is the same, the length is the same. The only difference is the current flows to the right in the top and then back to the left on the other one. So it's no wonder that everything is identical with the top and bottom segments except for the direction of the force. This is, of course, assuming that you have a uniform field. And then likewise, if we compare the left and right sides, that force, the force on each segment, the left, right, and the right segments, is going to be bigger, not because the current's any bigger, it's the same current circulating around, not because the magnetic field is any bigger, but simply because those segments are longer. And we found that the length of the wire matters. But once again, if this segment's longer, so is this. So these two forces, even though they're individually larger, they're going to cancel as well. So we find that the net force is 0 on a current loop in a uniform B external. Okay. Now, I certainly have not proven this for any general shape of current loop, but I'll tell you that the result is the same. Because it turns out that as long as the current loop, no matter what kind of crazy shape it might have, as long as it's in a uniform field, you can basically always take whatever loop you have and break it up into a series of opposing sides. Right? You can take this segment and pair it up with this segment, right? You can take this segment and pair it up with this segment, right? And so on and so forth. So a current loop of any shape really can be thought of as kind of a series of rectangles, right? So we find that the net force is 0 on a current loop in a uniform field. This, by the way, is not really a new thing. We discovered the same thing when we put, say, let me remind you, if we had a neutral conductor or insulator in, so this is neutral, doesn't really matter what it is, and we put that in a uniform field, right? E external. So uniform electric field. So we learned that it's not that nothing happens. We learned that the object undergoes a process called what? Charge polarization. So minus, minus, minus upstream, plus, plus, plus downstream. So it's not that nothing happens, but what is the net force on this object as a whole? Anyone remember? Nope. 0. So it's 0, exactly, because this is pulled this way, and this is pulled this way, but in equal amounts, so they cancel. So it's not the first time we've seen that a uniform field has no net force on something. And it's not a surprising result either, because we have a completely neutral object in a field that is exactly the same everywhere. So why would a neutral object prefer to be in one part of that field versus another part? It's a neutral object, and the field has no difference. No matter where you go, it's exactly the same. It was a different story when we made the field non-uniform, right? You guys did this with the packing peanut bits, right? So you took neutral bits of styrofoam, you put them in a non-uniform field, which, by the way, is more common than not, right? Because most objects make an electric field that does die with distance, right? It's not uniform to forever. So it charge polarizes again, but now the two forces are out of balance. the leftward part of the charge, half of the charge polarization is in a stronger field, and the right half, the plus half, is in a weaker part, so now the net force will be in what direction? Now it will be to the left. So now we have a net force because the field is non-uniform. So the common thread here is that if this is a uniform field, then the net force is 0. If it's a non-uniform field, then the net force is in the direction of the stronger field. Okay? And what caused this non-uniform field? Well, probably some kind of charged object, right? Because the field is stronger close to the charged object. So this was the principle of static cling, right? This idea that neutral objects can be attracted to charged ones. You guys attracted little styrofoam peanut bits, which were neutral, to some charged rod or whatever it was, glass rod or something. Okay, we could do that over here too, by the way. This field is uniform, but for instance, if we made the field stronger at the top of the page than at the bottom of the page, of course, this top force would be bigger than the bottom force, right? So then the loop would feel a net force, okay? So again, the net force will not be 0 on the current loop in a non-uniform field. So we'll get to that in just a bit. So watching the current loop get dragged around in a non-uniform field, but for right now I want to stay doing the uniform field. And the reason why is that there is going to be plenty of action in the just plain old uniform field. You might dispute that. What do you mean? This does nothing, right? This has a net force of 0. It'll just sit there. But there is plenty of action that will happen, as we will see, even though the net force is 0. And we can put it to lots of good use. I brought some toys today to show you why current loop in a magnetic field is a very useful and practical thing to do, okay? Or useful and practical thing to make use of. So let's figure out what the heck is going to happen here, because it doesn't seem like much. Now, in order to really show you what happens, I'm going to have to take this current loop, which of course looks like this. Well, I guess it looks like this. Right? So it circulates around. In order to draw this on the page without having the most interesting stuff be out of the plane of the page, one of the things I'm going to have to do is I'm going to have to draw the loop from the side view like this. Okay? So instead of seeing it face on going around, I'm going to have to draw it from the side view like this. So there's a circle with the dot there, indicates out of the page, of course. That's indicating that a current is flowing toward you. There's, of course, the arrows that go across, indicating that it's flowing this way. And then there's the end of the page, which indicates that the current's going to go like this. So if I draw you this side view here, I can draw 3 out of the 4 segments, even if I'm looking at the side view. So I have to give up on the one in the back, right? But if I draw this, I can look from the edge on view, right, what is going on. So let me sketch that. So I'm going to have a different perspective. I'm going to have that the external magnetic field is not into the page, it's to the right. And again, as I mentioned, it's uniform completely. I just don't want to have to draw it everywhere because there's going to be plenty of other stuff to draw, and I don't want it to kind of clutter up the works. So let me go ahead and draw what I just showed you. Draw one of these current loops from the side view. And let me not make it too big because I want to make sure not to run off the end of the board space that I have. So it looks like this. Current comes out, goes across, goes in, and then I can't draw the return current in the back because that's kind of the limitation of my drawing. But hopefully you remember, what is this? This is a side view of a current loop. So the current loop, instead of looking at it face on, I'm looking at it edge on. Okay? All right? So let's once again find the forces. Okay? So we have now some practice, more practice with the right-hand rule. Can never get too much practice. And finally, I think last lecture I felt like every single magnetic field was into the page, so we kind of were always slapping into the page. But now we don't, so we'll get some practice in different orientations. Let's start here with the left side here. The current is coming out, right? So you got to point your fingers out of the page. But then you have to orient your palm so that you can slap I into B. So B points that way, so I need to put my fingers like this. I slapped into B. See that? I slapped into B. So my force is going to be up. So on this segment, the force is up. So make sure you can get that. Definitely need to practice with the right-hand rule. Again, current comes out. I need to orient my palm so I can slap it into B, which points this way. Okay, see that? I into B. Force is up. Let's go over to the right side here, the current into the page. So my fingers have to point into the page. Then do the beauty queen handshake. Figure out how to slap that into B with the palm of your right hand. Well, it's already my right hand, but I got to make sure it's my palm. So I slapped into B, like that, with the palm of my hand. Force is down. And shouldn't be shocking to see the force just being the opposite direction of the one I did, because of course the current's reversed and everything else is the same, so the force will reverse. Now here's the tricky one. What about that current across the front? How can you slap I into B when it's already going in the direction of B? What do I do?
No force.
There's no force, right? Remember that if the charges are moving parallel or anti-parallel, there is no force anyway. So the front segment, the force is 0, and the back segment, it's also 0. Because those currents are moving parallel and anti-parallel to the field, and you have to have some component that's perpendicular for anything to happen. So notice that I've conveniently put all the action in the plane of the page. There's nothing actually going on with the forces outside the plane of the page. Now if you look at this, is the net force 0? Yeah, it is 0, right? You have one up force and an equal and opposite downward force. The net force is 0. And yet, looking at that, is that loop just going to stay there? What's going to happen? It's going to rotate, that's right. So this is where I remind you of your favorite topic, I'm being sarcastic, from Physics 1, which is torque. Okay? So remember we had two laws for extended objects. F net equals ma, but the a is really the acceleration of the center of mass. So what we have is if there's no net force on the current loop, that really just means the center of mass has to stay doing what it's doing, which is in this case at rest. So it says that the center of mass stays at rest. That's the only thing that the net force tells you. It tells you whether the center of mass can get picked up and accelerated and taken somewhere else. Can this object have, as we call it, translational motion? Can this loop just move one location to another? And because the net force is 0, it can't. But that doesn't mean that there couldn't be some rotation of the rest of the object around it. So here's the rotational version of Newton's second law. Torque, which is like the rotational analog of force, right? right? And angular acceleration, which we use the letter alpha for. So we do have that. So what can happen to a current loop in a magnetic field is that it can experience a torque. It can experience starting at rest rotationally and then suddenly spinning faster and faster. Okay? So let me remind you how we do torque. When you're talking about torque, it's always relative to a pivot. And in this case, the pivot is clear. It's the center of mass. Because the center of mass can't budge at all. So the only thing that the object can do is rotate around that pivot. So the pivot will be somewhere in the middle here. And then we characterize torques as either clockwise or counterclockwise around that pivot. So what's the direction of this torque? Is it clockwise or counterclockwise? It's clockwise. How about this one? Also clockwise. That thing is definitely not going to stay there. It's going to angularly accelerate clockwise. Now, how is it possible that the two forces, one of which is up and one of which is down, cause torque in the same direction? Well, of course, the difference is that one of them is not only in the opposite direction, but it's on the other side of the pivot as well. So that's how they can both rotate it the same way. So this torque is clockwise, and this torque is clockwise. And by the way, does anyone remember our sign convention for torque? When we say clockwise, how do we notate that? Does anyone remember? So remember, there are only two possible directions for torque, counterclockwise and clockwise. So how might we choose to, how do we always notate when there's only two possible directions? Plus and negative, plus and minus. So does anyone remember what we picked clockwise as? Counterclockwise is positive, that's right. So when torque is positive when it's counterclockwise and it's negative when it's clockwise. Okay? So in this case, we're going to have a net torque that is going to be in the clockwise or negative direction. Okay? So this thing is going to rotate. It's going to not stay at rest rotationally. It's going to stay at rest translationally, which means the center of mass doesn't just pick up and move. It's not going to do, loop's not going to drift somewhere else, but it is going to rotate in place. So what I want to do is I want to follow this rotation and see what becomes of it. Okay? So let me draw it again. When it's rotated a little bit, so it's rotated just a little bit. Sorry, I drew that really close to the previous one. So hopefully that's not too cluttered. I also want to make it clear, I'm not indicating that the loop is going to the right. I'm just drawing it further to the right on the board because obviously I can't draw all this stuff on top of each other, right? It's just rotating in place. It's not moving to the right. I'm just trying to draw a little bit of a time lapse, okay, of this rotation. Okay? So let's do the right-hand rule once again. And I will point out, we've actually, even though the loop is rotated, the current here on the left side has maintained its orientation with this field, right? So this is out of the page, this is still out of the page, right? So same current, same field, the force is exactly the same way. It's still like this. If that bothers you, just isolate that one current and you'll see it's the same exact thing as before. It hasn't changed. That current is still coming out of the page. Likewise over here, that force is still downward. So we find something interesting. These forces are still rotating it clockwise, but notice that they're sort of falling off tangential path, right? These forces are no longer completely tangential to the circle, right? So one way you can visualize this is if this wasn't a current loop, it was a panel of a revolving door, right? And you and your friend are both going to rotate it together from opposite sides. Now, if you're using a revolving door, you don't just push in one direction, you follow it, right? You go around like this, so you can stay tangential to the thing, right? But these forces are not obliging, right? These forces don't change their directions, so they're falling off of the tangential path, right? Does that make sense? In fact, by the time we get over here, when they're like this, the forces at that point are going to be completely radial. They're going to look like this. So if you and your friends try to pull on a panel of a revolving door like that, nothing's going to happen anymore, right? So what we have here is we've reached a state where the net torque is actually 0. I guess we should probably mention here that the torque at the first case is maximum. I should probably put it down here. So here the torque is maximum. You can see that the forces are oriented perfectly tangentially to the circle. And over here, the torque is 0, which is the minimum. So the torque is certainly not uniform on this thing. Oh, and before I go too much further, of course I should readdress the front and back segments. The short of it is that they don't end up mattering. For instance, let's do the front current here. It's going to be a relatively short slap, right? Remember, it used to have no angle at all to the magnetic field. Now it's just going to be I is a little diagonal slapped in a B, right? Short slap, forces out. Well, guess what? The force in the back is going to go in. They're going to just cancel. So the front and the back segments, they're not going to be 0 individually, but they're going to cancel. So I really have tried to put all the action into the plane of the page. So we've reached a state of 0 net torque. If we let it go from there, nothing would happen. And by the way, this orientation happens to be this orientation that I first drew. I know might have to think a little bit about that. But notice here that the loop looks like this, and the magnetic field is coming directly like that. So if you rotate your view, it's this, right? So this, not only was the net force 0, like in all these cases, but this I happen to do was really the orientation where there's no action. There's no torque here either. So if you release something in this orientation, it would just sit there. It would experience no net force, and it would experience no torque either. So it would just sit there. That really is the most boring thing. Okay? This orientation is when the net torque is 0. So of course I wanted to first get that out of the way, why the net force was 0, before I started to put this thing into an orientation where the net torque starts to not be 0. So if I release something from rest like this, it would do nothing. However, I'm not going to release it from rest there. I'm going to release it from rest here, which means it's going to initially get torqued clockwise, a little less so here, but still clockwise. And when it gets here, yeah, it's not going to stop dead, because even though the torque turns off, you've built up all this angular velocity in getting there, right? So you're going to overshoot that. So you're going to go something like this. So now, let's find out what happens as you overshoot this orientation of net torque being 0, well, I draw in my forces once again. Remember, the force directions haven't changed. What's going to happen there? It's going to slow down because the torque is, what's going on with the torque?
Reversed.
It's reversed, exactly. So the torque is now going to have reverse direction. So here, the torque is in the opposite direction, which is counterclockwise now, than it was before. What does this remind you of? If there's a system where it speeds up going towards a location, then when you get to the happy place, it overshoots it, but then starts to get pulled back.
Pendulum.
Pendulum. It's a perfect analogy for this system. Okay? So a current loop in the magnetic field acts like a pendulum. Let me do a comparison. Play by play. So I guess I'll label these guys. I'll label this orientation A, B, C, and D, so that I can draw the corresponding pendulum positions. So here's my pendulum. Of course, here's the happy place, hanging straight down. It experiences no gravitational torque whatsoever because the force of gravity is, of course, entirely radial, right? It's pulling straight down from the hinge, right? So which orientation is that like? A, B, C, or D? C, right? So that's the happy place. If you let a pendulum go from there at rest, it won't be much of a pendulum. It'll just hang there, right? Just like if you released a current loop in this orientation, it would just sit there, okay? But if you release a pendulum from anywhere else, it's not going to swing down and then stop there. It's going to overshoot, right? Because all the velocity you built up getting there is going to now cause you to overshoot. You can, of course, displace it from there just a little bit. I guess this would correspond to, let's see, this would correspond to B, I think, right? Because the torque is going to be clockwise, which is negative. Just a little bit, right? I guess D would be a little bit on the other side, where the torque over here is going to be counterclockwise or positive. Can anyone tell me what A would look like? Yep, dead horizontal. A would be like this. Now, why is that? Because remember that if you have a pendulum that you release like that, the force is perfectly all tangential, right? Just like it was in my orientation A, those magnetic forces were perfectly lined up along the circle, right? It's at orientation B, right, where the force is falling off, of course, in this case, same reason, right? The magnetic forces weren't obliged to change along with you tangentially, right? So they started falling off the tangential path. That's the same thing with gravity. Of course, gravity always pulls straight down, so it's not going to always act tangentially to the pendulum, right? Until we get down here, and of course here the force of gravity causes no torque at all. The analogy is pretty perfect. In fact, you could probably tell me, if I release this pendulum from rest at point A, so it was like this, where would it stop again and turn around? Like that, right? And just go back and forth like that. That's the same thing with the current loop. If I release it from rest like this, it'll go faster and faster until it rotates into this orientation, start slowing down, go like this, right? So just kind of like a pendulum. Does that make sense? We're going to put this penduluming behavior to good use, okay? Or the fact that it's willing to torque to good use, I should say. So the first thing I have to do is to tell you that there's a big shortcut for how to handle these current loops. It's going to be your friend. Very shortly, we'll never draw one of these monstrosities again. Okay? Here is what we do. We need a shortcut to discuss a current loop. So here's what we do. This is our first use of what's called the right-hand rule number 2. Now, if you're groaning that we have more right-hand rules to do, this is the easy one. Okay? So right-hand rule number 1 is hard because it's a slap rule. It's one thing slapped into a second thing, and the thumb gives a third thing. So that's 1, 2, 3, right? 3 different things that you're relating. This is relating 2 things. I call it the curly straighty. If you can make a thumbs up, you have done it. Okay? So if something is curling around, you go with your fingers like this, and your thumb is the other thing. So curl straight. That's it. So what am I going to do here? My current is certainly curling around, right? It's wrapping around. So what I do is I wrap my fingers around the rotation direction, and my thumb gives something. And this something is called the normal vector. This is not to be confused with normal force, by the way. This is not a force. It's nothing, actually. It's just a tool. Okay? What's sticking out of the current loop? Nothing. It's a mnemonic or a tool, and I'll show you it's an amazing tool. Okay? So, what is this thing? Well, think about it like this. With a single arrow, right? With a single arrow, someone can just say, here's an arrow. And that arrow tells you everything you need to know about the current loop. Because it tells you not only where is the current circulating, it's rotating in this plane, and it also tells you in that plane, which way is it going around? Is it this way, or is it this way, or is it this way? Not this way, because the right-hand rule doesn't go that way. So you think about it, with a single arrow, you can encapsulate information about what plane the current flows in, and which way around that plane does it go. That's pretty powerful. Okay? So again, wrap your fingers around the current direction, and your thumb gives this thing called the normal vector, which is just a tool. Okay? Let me write it down for you for your reference. Let's see where I can sneak it in. So this is right-hand rule number 2. We'll have several applications for this right-hand rule. So that's why I just generically call it the curly straighty. Okay? It relates 2 things, one that circulates and one that's straight. And the straight arrow will always point perpendicularly to the entire plane of the curling thingy. Okay? So in my case, what I'm using it for, if the current circulates like this, then wrap my fingers around the current, and my thumb gives this thing called the normal vector, which I guess I'll use some fancy notation for it. I'll do it like that. I'm just doing that because, don't worry about what that symbol is. It's far beyond the scope of the course, but I really don't want to write out normal vector. It's too many letters, okay? So that points like that. It's the normal vector. It's not a force. It's not anything. It's a tool to discuss, I should say, shorthand for discussing the orientation of a current loop in space. Okay? So if I give you any normal vector, you immediately should associate this should be replaced with this. Okay? So the current flows around like this, the normal vector points like that. Okay? So that's what you have to imagine. This arrow can be a stand-in for this current loop. I'm going to throw it in right now. Let's see. So there's my current loop, like that, right? So that matches up with that. So apparently my normal vector looks like this. Notice it's perpendicular to the entire plane of the loop, or the current, right? I can draw it over here. It looks like this. I can draw it over here. It looks like this. I can draw it over here. It looks like this. I forgot to label it here. I guess I can do that. I guess I don't really need to label it because it's all green, so the green is the normal vector. Okay. Wait, that's great. The normal vector is a stand-in for all this stuff, so we could really erase the current loop at this point. How does the normal vector seem to want to go relative to the magnetic field? What's its preferred location or preferred orientation? What's that? With it, that's right. When the net torque is 0, the normal vector points in the same direction as the magnetic field. That's easy to remember, right? How does a current loop want to orient in an external magnetic field? Well, the normal vector wants to align with the field. Okay? So we can write that down here, is that the normal vector wants to align with the external. We could, while we're on that subject with the pendulum, right, why don't we define an arrow for the pendulum? Why don't we define like an arrow which describes a pendulum that looks like this, right? We'll just draw an arrow that points from the pivot to the end, right? So we find the same deal, right? When that arrow points in the same direction as the external force of gravity, or you could talk about gravitational field. You haven't usually, but you could. When the pendulum arrow points in the same direction, that's the happy place, right? Does that make sense? And likewise, I can draw myself a little shorthand diagram. Of course, this is kind of sideways, but let's change the magnetic field orientation like this. So it's downward, so we can have the analogy with the pendulum be perfect. Then this is how something would want to orient, right? So this is the zero torque orientation. This would be my, so it would, if I let it go here, it would want to rotate until it was like this, although it might overshoot, of course, and then come back, right? So just like a pendulum will pendulum around some equilibrium orientation, a current loop will do that as well. And the equilibrium orientation is when the normal vector lines up with the fields, okay? Does that make sense? Okay, so once you've gotten those concepts down, and the concepts are the most important, I'm just going to give you the equation. I'm not going to derive it because it's probably not really worth it. But basically all we would do if you're interested and bored on a Saturday night at some point, how do you get the torque formula? Well, you of course take these magnetic forces. We know the equation for that. Did it last time. Force is ILV sine theta. And then you plug those in to your torque formula from Physics 1, and you get this equation, which I'm about to give you. Let's just cut to the chase, okay? So that equation, I'm going to have to clear some space, so let me clear the minimum space that I need. So this is the magnetic torque on a current loop. I want to talk about the size, and I want to talk about the direction. The direction part, let's get that out of the way first because we've already done it. We said that the direction is such that the normal vector wants to align with the external. That is the direction the torque will always be. It's not always clockwise, it's not always counterclockwise, it's whichever direction is toward the happy place, right? Just like a pendulum, right? Here's your pendulum with a happy place. If you're to one side, it'll torque counterclockwise. If you're to the other, it'll torque counterclockwise, right? It's always toward the equilibrium. And in this case, the equilibrium is when the normal vector is aligned with the magnetic field. Okay? So let me give you a formula for the size. Seems like there's a lot going on, but most of this stuff pretty straightforward. So, I, it's the current in the loop. No surprise that that will matter, right? Because you have to have current flowing in order for the magnetic force to initiate this torque. The B here is the B external. I guess I can write it as B external, or let me just be lazy and just say B. Okay. So what is this other stuff? A, haven't seen that one before. A is actually just the area of the loop. So for instance, if the loop is a square, you can use L squared, if it's L on a side. If it's a rectangle, you can use length times width. Maybe it's a circle, you can use pi r squared, or whatever. It's the physical size of the loop. Any closed loop is going to have some kind of area, right? And then, the n is just the number of loops. So that gets to be like your multiplier in the front. So think about it like this. If you have a certain amount of torque on one loop, then 10 loops will have 10 times that torque. So we almost inevitably, in any application, don't just have one loop. We will put a whole coil, because then we get the power of numbers, right? So if you have 10 loops or 100 loops, you have 10 or 100 times the torque you would otherwise, right? That make sense?
Is that why electric motors have?
Yes, yes it is. Yep. Because think about it, right? If you have a bunch of turns of wire, let's say 1 amp running through this wire, and then you turn it around a bunch of times, well, having 100 turns of 1 amp, that's as like having 100 amps. Now 100 amps is dangerous, but you don't really have 100 amps going through any single wire, right? It's partitioned off in a bunch of wires, right? So it's the same current basically getting counted multiple times, right? So we inevitably, in these applications, always have a bunch of turns, and that's why I'm putting it in the formula now. I could, by the way, have even put it in the formula for the single strand of wire. Remember we talked about that last time, ILB sine theta? If you had a whole strand, series of strands running together, just multiply it by n. There might be one homework problem where you need to do that, by the way, so I should tell you that. Okay? So anytime you have not just one, but a bunch, you multiply it by the number you have. It's pretty straightforward. Is that okay? The final factor, so we've covered the number of loops, the current in those loops, the area of the loops, the area of one loop, the magnetic field that they're in, and then the final one is, of course, going to account for how is it that the loop is oriented in the magnetic field. And we do that by measuring the angle between the normal vector and the magnetic field. That accounts for the fact that sometimes the torque is nothing, sometimes the torque is something, and the torque may even be maximum. So all you have to do is measure the angle between the normal vector and the magnetic field. So for instance, let's do this one. If this was the normal vector, and this was the magnetic field, what angle should you put in the formula? 90. So there the angle would be 90. And sine of 90 is what? What is it? 1. Which, again, we said that was maximum torque, right? You experience the maximum torque when the normal vector is perpendicular to the field. Unfortunately, I had to erase it, but it was the orientation A that I had up earlier. What about over here? When the normal vector is like this, what's the angle between the normal vector and the magnetic field? 0. So theta is 0. What's sine of 0? 0. So no torque. So it seems to be working out pretty well. It's a very quick shortcut. All you have to do is, if you're comfortable enough finding the normal vector of the current loop, just by wrapping your fingers around the current, then measure the angle between that normal vector and the magnetic field. If it's 90, so if the magnetic field is like this, it has a loop like this, that's maximum torque. If it's like this, it's 0 torque. If it's like that, it's something in between, right? Okay? But we find something interesting. There's also another, remember the angle between two vectors can range from 0 to 180. What's sine of 180? Does anyone remember? It's 0 as well. So apparently, there's another equilibrium. What's up with that? We should look at that. Okay? So sine of 180 is 0 too. So what's up with that? There are two equilibriums? Let's find out.
Isn't that the parallel, anti-parallel thing?
That's exactly right. So let's sketch that. That's why I've been saving these guys. What if, instead of like this orientation C that I have here, what if instead of the normal vector pointing with the field, what if it was like this? Let's take a look at what would happen there. So I'd have to draw that. All the currents would look a little different. Everything would be reversed. The normal vector now points to the left. And the forces, of course, let me borrow those. So when the current was out, the force was up. And when the current was like that, the force was down. Sorry, I should color code these a little better. So let me see if I can sneak in here with another color. So here are my forces. No, I don't know if that's more or less helpful. So this is when the angle between the normal vector and magnetic field is 180. Let's look at those forces. The force is now radially inward. Is the torque 0? It is. We've found another equilibrium. So not only does the normal vector have 0 torque when it's aligned with the field, but also when it's anti-parallel, aligned but against it. So, is this where we run out and say, well, this isn't quite like the pendulum? Well, it's exactly like the pendulum, because a pendulum has one of these too. If I call this, what letter am I on? E? Let me call this orientation E. What would that look like for the pendulum?
Straight up.
Straight up. We have to imagine our pendulum has a rigid rod, right? Is it technically true that that would stay there if you set it there perfectly? Yeah. So even the pendulum has another equilibrium. So there are two positions on a pendulum that also would experience no torque. But we want to say our gut reaction is those are different, right? Yes, there is zero torque in both cases, but they seem very different. And the reason, of course, why is because if you take this pendulum and you move it a little bit, it'll come back, right? But if you give this a little poke, it ain't coming back, right? It'll fall over. So they're both zero torque orientations, but we call this a stable equilibrium, and we call this an unstable equilibrium. So the difference is not just that the torque is zero, but if you slightly perturb it, will the torque bring it back? Will the torque that you incur bring it back or take it somewhere else? Now if you don't believe me, let's try it with our system here. So let me take this guy right here. So here the forces were outward, right? So the forces were outward. So what happens when you take, if you have an upward force and a downward force, and they're both outward, what happens when you take this pendulum slightly off of its path? Well, the forces return it, right? You take it off a little bit, they'll pull it back. Let's take a look at this one though. Okay, looks like this. And the forces are inward. What happens when the forces are inward? Yes, it stays at zero torque, but what happens if it slightly moves? Right? So it's not going to come back. So the analogy to the pendulum is perfect. Okay? There are two zeros, two places of zero torque. One is at 0 degrees, that's the stable place, and one of them is at 180, which is the unstable place. You can think of it like the same way as a pendulum with the pendulum thing up here. Basically, it'll stay balanced because it doesn't know which way would be the best to get to the happy place. Okay, paralyzed by indecision, okay? I'm straight up. I can't go straight through the pivot to get where I want. I'm just going to need someone to break the tie for me, right? If you poke a little bit this way, it'll go like that. If you poke a little bit the other way, it'll go like that, okay? Does that make sense? Okay, so I know that that is a lot to chew on, but I'm just about to show you why it's important that we take the time to understand the behavior of a current loop, because we can make a lot of very, very useful devices out of it, okay? So again, just to summarize, the natural tendency of a current loop in a magnetic field is to experience torque. That torque will be such that the normal vector wants to align with the field. Generally speaking, if you release something at one of the equilibriums, it'll stay there, but if you release it from anywhere else, it'll torque into the preferred orientation and then start penduluming around that. Okay, so let's take a look at some practical uses of this. This first one, let me put it up on a stand so you guys can see a little better. So here's what I have. I know it's hard to see, but there is a current loop that is sitting in there. It's sitting flat like this, okay? Some of you that are up close may be able to see the winding there. So what I'm going to do momentarily here is I'm going to send current through it. So if I send current through it, the normal vector will point like this. This little coffee strainer, okay, this is a little coffee stirrer, is basically a proxy for the normal vector. Okay, so instead of having this fancy plexiglass thing, oops, the normal vector would be like this. So wrap your fingers around the current, thumb goes like this. Instead of this fancy plexiglass thing, it's a little coffee strainer. Okay, current's not in there yet. The magnetic field is, there's magnets here, and there's one magnet over here, another one over here, causes the magnetic field to go like that. So it's exactly the same orientation as we had on the board. So we have normal vector initially like this, magnetic field like this. My let me send in some current. How am I going to do that? Well, that's not that exciting. I have a battery where the current's going to come from, and then I have a resistor, which is a variable amount. I can turn this knob and change the amount of resistance. Right now it's cranked all the way up, which means, of course, lots of resistance, so not very much current, right? In fact, it's minuscule, vanishing small amount of current. So let me turn down the resistance, and then I'm going to let some current in there, some appreciable amount of current, and see what happens. So you see it trying to rotate, right? Now, why is it that it didn't just start penduluming? You can see why right in the front there. Why is that? What prevents it from just going like this? It's a spring, right? So eventually the spring is strong enough to stop it from rotating further, right? So, of course, it becomes a competition between the magnetic torque, said, I want to align with the normal, and the spring says, get back here, okay? And of course, the more current I send through, the stronger the magnetic torque becomes, and the more the needle can rotate. And if I take the current down or even off, then the spring wins and brings it back like this, okay? So, it's kind of, you might think, oh, that's kind of a neat little toy or whatever, but this gives me a way of visualizing, turning into something I can see with my own eyes, how much current is going through that loop, right? If more current is going through there, the needle goes more like this. If less current goes through there, then the spring brings it back. What is this thing? It's an ammeter. So what you do is you get yourself a little dial here, okay? And you send known currents through it, right? You have some device where it tells you, oh, I'm sending in this many amps. And then you see where the needle goes for that many amps. You put a little label on it. Okay, that's that many amps. So that later, when you don't know how much current you're sending through there, this can tell you because the needle will go in the same place. So we've just built an ammeter out of this principle. Okay, you can see someone has already been doing this, right? Labeling various points with various currents. So you calibrate it with known currents. The needle goes here when this current is so much, and then you work it backwards later, right? If the needle points here, that's how much current you have. Okay? This, by the way, was built for me in the spring by some students. So there's not much to it. It's just a wire winding, a magnet, and a coffee stirrer, okay, and a spring. Okay? They did do one nice refinement. You may notice that in addition to the coffee stirrer, there is a little piece of mirror here. That's because for them, they wanted to create an ammeter with more precision. And for them, they didn't want to just use a coffee stirrer, they wanted to use a laser. So you can bounce a laser off the mirror, and I know this is not going to be visible at all in the video, and maybe not for some of you, but you see up there's a spot on the ceiling, right? You see that green spot on the ceiling? Okay. So what's going to happen to that spot when the mirror rotates? It's going to move. So let's try it. If I can get it to be there in the first place. Geez, I can't even hold still. Let's try to help myself with a little bit of... All right, I'm going to try it. I can't seem to... You want to help me here? Try to hold that thing steady so that we can see the spot on the ceiling. There's a button right there. Yeah. Okay. So, oh, it's hitting your hand. So you gotta give it a little clearance. Okay. So we see the spot and we rotate it and oh, why is it? Oh, I'm rotating it the wrong way. Oh, you're drifting off the mirror. You might have to sacrifice yourself to this demo, not be able to see the spot. Okay. Make sure it doesn't hit your finger. Oh, no? No spot on the ceiling. Okay. And then keep it there and there, whoa, there we go. You can see a lot more precision, right? we can put a bunch of hatch marks in the ceiling. This spot is this many amps. So we have to put the laser on a stand though, right? Because it's way too hard to hold in your hand. Okay. So if you're interested, my students, they did a whole presentation. They built this and then they did a whole presentation on this. It's called the laser assisted ammeter. And the poster that they did is right across from my office in a poster case in the hallway. So you can see that's a really useful thing, right? That's something useful and practical you can build out of this. Okay. Are there any questions on this? Okay, so again, we're not penduluming per se, right? But we're using the idea of the rotation, right? So we're countering what would not otherwise be penduluming behavior by the spring. So I'll put this in your lab probably when we're doing the magnetism lab, which will be not quite yet. But for those of you that either couldn't see this, either because you're in the back or some people that are going to be watching it at home, I'll put this out and you can play around with it. Okay, it's fun. Fun times.
Okay, so the audio cut out here for just a second, but I'm pointing out this device. There's the battery underneath. There's a D battery inside there, and there's two prongs just sticking up, and it just lets us raise the positive and negative terminals up. And then there's going to be a piece of wire, a wire loop that's going to go on top there.
The magnetic field is this little button magnet. So let me go ahead and do that. Of course, you need the loop on there to make contact. See if I can get it going. Really wants to sit in that orientation. Okay. What is this thing? It's a motor. So what is this? I have a little button magnet, I have a piece of wire, and I have a battery. Okay. Now, the obvious question, it's not penduluming at all. It's continuously rotating in the same direction. So, well, how is it doing that? It should be going like this, right? Well, you can get it to rotate the same way just by a bit of trickery. It's not the physics are any different. It's just a bit of trickery, okay? Let me explain how that trickery works, okay? So remember that the normal vector only exists when there's current in the loop. So here's how that thing works. This thing, by the way, is called a DC electric motor. DC standing for direct current. All of our circuits so far have been direct current, meaning that the current flows in a single direction. So how does this thing work? Well, the way it works is this. If the magnetic field, let's say, is like this, just doesn't really matter what direction. In that motor, it's more up than anything. So let's say I release it like this, with the normal vector, like so. So which way is this going to experience torque? Clockwise or counterclockwise? What is it?
Clockwise.
Clockwise. Because it wants to align, right? So it's going to look like this. It's going to experience torque until it aligns with the field. So then, how is it that we keep it from slowing down as it overshoots the equilibrium and wants to bring it back, right? Well, here's what we do. We just turn off the current. Just let it coast. We just let it coast until we get back over here. So there's no normal vector at this point because there's no current. So I'm just kind of drawing like a ghost normal, right? This is what the normal would be if there was current. But from here to here, the current is 0, so there is no torque. It's just going off inertia. When do you think we turn it back on again? when it gets back to where the torque would be in the same direction. So from here to here, the torque is going to be clockwise. So you see, we basically torque it in one direction, and then when the torque would be back in the other direction, we just turn off the current, and we turn off the torque, and we just let it coast. It's like a one-armed motor, right? It's a motor that's really only being pulled half the time. The other half of the time, when the torque would be slowing it down again, we just eliminate it, okay? So half the rotation, it's being torqued in a direction, and the other half, the torque is turned off.
Pedaling a bike with one leg.
Yeah, it's basically, that's exactly right? It's like pedaling a bike with one leg. That's a great analogy. So the question then is, how did I do that? Well, this thing here, I know that the insulation on the wire looks almost like metallic, but there is insulation on this thing. And what this thing that has, it's deceptively simple. It's actually hard to do this in practice. The insulation is scraped off very selectively on the ends. So if you were to look at the axle, okay, so if you looked at this current loop, notice that these cradles on the ends don't have a top. They have it's like a notch. It's not a complete circle. So if you looked at the ends here, here's what you'd actually find. You'd see that here is the notch in which the wire sits. You'd find here is the wire. This is like looking at the end of the wire. And here's what you'd see. You'd see the insulation is only on half, right? So half the rotation, it makes electrical contact. And then the other half, so this is where current can flow in. But then, half the time, the insulation rotates in between, like that, and it prevents current from flowing in there, and the current's zero. Pretty clever, right? That's just a parlor trick for making sure that the current is always flowing in a direction as to cause a torque in the same direction. Now, this is, of course, our battery. The current will connect it in a certain way so that the current flows around from here to here. And then when the insulation goes on there, we won't send any. Anyone have any suggestions for how to take our one-armed motor and turn it into pedaling with one leg, and how we can pedal with both legs?
Would you shave off insulation on different sides? Like one facing up, one facing down?
That would be problematic, because if one of them is insulation, then it can't go through, right? Any ideas? It's not an easy answer. You just have to realize it, and then you're like, oh, that makes a lot of sense. So over here, when we have this turned off, and we're not doing any torque, of course the problem is that the torque would be the wrong way. So what could we do to make sure that the torque was still the same way? What would we have to do for the torque to be the same way?
Rotate the magnet too.
That could be true, but that's not an option in this device, or this particular type of device. You could reverse the current direction, right? If you reverse the current direction, then the torque stays the same way. So let's just reverse it from above. So if we reverse the current direction, then the torque will stay in the same direction. Right? Does that make sense? So how do we reverse the direction of the current? Well, when it would be zero, how can we get the current in there? We can't get it in here because the insulation is blocking, but let's put it in the top. Right? We'll put another set of these, only the notch will be on the bottom. right? See what I'm getting at? So this one, if the notch is here, it'll make contact when the insulation's on the top. But here we can put another one when it's not going from this set of contacts, it will be coming from this other set. So we'll just put another set of these, right? It looks something like this. And from that, we'll send the current, when it's in contact with those, we'll send it the other way.
So basically what they call brushes in the motor.
Yes, this is exactly what this is called. This is called a commutator. A commutator is just a clever parlor trick. So commutator, that's the fancy word for this. This is just a clever parlor trick so that every time it rotates 180 degrees, you click onto the other set of contacts where the current is sent the other way. A very typical way of making contact here, because obviously you're making contact with a spinning axle and a stationary contact, a very typical way of doing this is by having brushes. So that way there's not as much friction, but you can still make electrical contact. So you just have these very fine brushes, right, which don't rub as hard onto the contacts. You can even do this with the same battery, by the way. The same battery, you can just connect the contacts the other way and send the current. So you don't even really need two batteries. I mean, you could use two batteries, but why would you, right? Just have the current sent through one way by the battery, and then when it rotates through 180 degrees, use the same battery to send current through the other way. The batteries always happen to send current from high voltage to low voltage. You just have to connect it so that it goes the way you want. Okay? So hopefully I've impressed upon you what a useful system the current loop is. This is just in a uniform field, so there's no action besides torque. And yet we can put that to good use. We can use it for making an ammeter. We can use it for making an electric motor. Lots of good things that can be done here, because the whole idea is that the magnetic field allows that current to be deflected, and what that means is that we will see some kind of rotation. So that rotation, we can put it to good use. Of course, here, once we have this going, we can attach the axle to just about anything, right? Attach it to a spinning blade, it's a blender. Attach it to a wheel, okay? You can use an electric car, right? Now, there's different types of motors. This is just one. This is not even the most common one, but the principle is the same, okay? We use some kind of magnetic deflection to cause electric current to become motion, okay? That's the principle behind the motor. Okay, so let's knock off there for today. We'll pick it up next time.